Welcome back. So in the last class we have started our discussion on closed loop control of our 3-phase VSI. So where we have seen that what is the requirement of your DQ frame control, what was the advantage of that. So in 3-phase AC where we will be having high power chargers, there we have to go for 3-phase AC as per the grid requirement. So when we connect 3-phase AC to our charger, so there we having interest in controlling two parameters, that was our active and reactive power flowing through the charger or exchange with the grid. Whereas we had three variables, that is our three phase currents which will be drawn by the converter or exchanged by the converter. So to avoid this more number of variables, that is three variables to control two parameters, we have gone through our alpha beta and DQ frame. Alpha beta was our stationary reference frame where we had got two quadrature sinusoidal components, but the PI performance was better when we give DC signals to it. So that's why we have shifted into our rotating DQ frame where we get the three phase system mapped to two constant DC signals, where one of the components will be controlling the active power and other component will be controlling the reactive power, and both will be independent from each other. So that's what was our main motivation behind going into our DQ frame. So this shows the model of the three phase VSI, where this is inductance and the resistance which is present in between the converter and the grid. So L di by dt plus R into I, that will be the drop which will be occurring in this series connection of L and components. So that will be equal to the difference between the voltage applied across each terminal, or that is the voltage between these 2 points. So what will be that? So that will be the voltage generated between this, suppose first phase. So it will be the voltage between VRO and the voltage of the grid. So it is written as S1 minus S4. So those are the status of the switch. So if S1 is on, this will be mapped to your VRO will be equal to V0 by 2. So we will be writing, when S1 is on, we will be writing 1 in place of S1 status and 0 in place of S4. They are perfectly complementary devices. So when one is on, the other one will be off. This equation is the model of our A phase of the circuit, then the B phase, and similarly the C phase. So these three equations are in the ABC domain. Now if I map it to the DQ frame, so I have got two equations and we have seen these equations and their relation with the power being transferred. Okay. So when I follow the same procedure to calculate the sense the voltage at the PCC and current at the PCC, and I convert it into the DQ frame, I will see that the active power will be given by this relation and the reactive power will be given by this relation. So we wanted one of the component, that is D or Q, based on which frame we have selected to control our active power and reactive power independently, but we have got some type of coupling between them, that is both the components, that is active and reactive power, now depends on the two frames, that is D and Q. So because of that we have seen the requirement of this decoupling terms. Okay. So now this decoupling terms are there. Now this Vd and Vq are our feed forward terms to improve the response hour of our closed loop system, and this is divided by VDC by 2 to make it into per unit, or the calculating the modulation index, which will be ranging between 0 to 1. So if we are not going for per unit system, then this term, this division can be avoided. Okay. So it depends how the control system is supposed to be designed. If you are going for actual values, then we will not require this division of VDC by 2. If you divide it by VDC by 2, which is the maximum peak value which can be obtained from this converter with a supply of VDC, so it will be giving us an value limited between 0 to 1. So we will be getting an per unit output from this reference frame, or else if we are not going for dividing this, we will get the actual values, whichever is the voltage rating, based on that we will get the actual values of the parameters, that is our modulation index MA, MB, MC will be in the actual values. Now, so this is just the inner control loop of our closed loop controller. Okay. So generally we will have an outer loop which will be giving us the values of this ID reference and IQ reference. Why we will have this outer loop? Because our main parameter which was to be controlled was active and reactive power, but now we have got an intermediate parameter, that is ID and IQ. So how to calculate this ID and IQ values? That will be done from the power reference. Okay. So, in this case if you see we have this yellow box is your outer loop control loop. Okay. So, this inner control loop sometimes it is called as decoupled current controller because of this removal of the coupling terms. This has become decoupled, that is the change in one parameter will not affect the change in the other parameter. So, sometimes it is called as vector control, vector current control, decoupled current control, DQ frame current control, everything is the name of this control system which we are seeing. If you see now P reference is compared to P actual, where we are assuming that the D frame is responsible for active power flow control. So, here P reference has been compared with P actual, the error will be passed, that error will be giving us the required ID reference value. Now, we are comparing this ID reference value with the actual ID to calculate the error which goes into the PI controller, and ultimately our voltage and its angle will be adjusted as per the command given for the active and reactive power respectively. So, similarly if you see the lower circuit, there we have the reactive power reference being compared with our actual reactive power, that will be giving us the reference signal. So, this is outer loop which gives us the command or required information about the currents, because it is a voltage source converter. The voltage polarity will be fixed. Now, we will just change the current direction to control the power flow in both the directions. So, if current is positive, that is it is having a phase shift between 0 to 180, we will see that the active power will be transferred in one direction. When it has the opposite case, the power will be reversed. So, only the current direction will be changing, the voltage polarity will be fixed in voltage source converter. So, that is why we have generated the current reference based on our active and reactive power requirement. Okay. So, these are not only the possible inputs for our outer loop, we can have other inputs, that is VDC. We can use or indirectly calculate the active power requirement by comparing the reference DC bus signal with the actual DC bus signal. So, what is the philosophy behind this? So, if my power being drawn by the charger is different from the actual requirement of the electric vehicle charging power. So, what will happen? So, if excess power is drawn from the grid, so the DC bus capacitor, so it will be star at the reference. Okay, so and DC actual. So, that also can generate the ID. Similarly, for reactive power, with the other option can be your VAC compared with your actual value of the AC voltage, that will be giving me IQ difference. These are the two other options which can be used as per the requirement. So, how this DC value will be giving us the active power required by the charger, that is indirectly if we see. So, we have, let us go back to this circuit. So, in this case, so we will be having a preceding stage which will be converting our DC bus signal. So, this is the DC bus. Okay. So, this will be the intermediate state. After that, we will be having a DC to DC converter which will be meeting the requirement of our battery voltage, because the, as we have already discussed, the SOC of the battery will be changing. So, its terminal voltage will be changing. So, now this DC to DC converter will be responsible for maintaining the difference between the DC bus and the actual requirement from the vehicle. Okay. Suppose now let us consider that as a load for us for this stage, that is for our 3-phase VSI, we will consider that as a loading. Okay. So, now suppose the load requires some X amount of current, but by mistake our controller has drawn X plus delta X current from the grid. So, what will happen now? The voltage will be rising, the DC voltage will be rising. Why? The power which will be drawn, it can be done by using X amount of current, but delta X current has been coming in excess. So, that X will be absorbed by the capacitor and it will charge. So, our DC voltage will increase when we are drawing excess amount of active power from the grid. Suppose the other condition, suppose I am drawing less amount of active power required for the flow of your power. So, here now what will happen? This negative delta X or the deficit of current will be supplied by the capacitor. Okay. So, what is the meaning of minus delta X? Capacitor is behaving as a source and ultimately it will get discharged. So, if I am maintaining this VDC, so what is the meaning of that? Whichever power is coming from the preceding stage is given to the follower stage, or the front end, whichever power is drawn at the front end, it is being given to the load. So, neglecting the losses in this analysis. So, now this, that is why our VDC can give us an indirect estimate of the active power required by the circuit. Similarly, VAC, the reactive power is mainly responsible for maintaining the AC voltage. So, this also can be used to indirectly calculate what will be the requirement of reactive power to maintain the AC grid voltage at the reference value. So, now after this MA, MB, MC will be achieved by us after we are going for the reverse transformation. This MA, MB, MC will be compared with the triangular signals to calculate the gate pulses. So, we will be comparing the triangular signal with this MA, MB, MC. The output will be MA, MB, MC. So, they will be compared with the triangular signal and the gate pulses will be generated. So, this is what is the closed loop control of your 3-phase VSI. Now, let us see some additional topics in this AC to DC conversion, and before that we will go through the various terms which are generally used in our electric vehicle applications. First is your grid to vehicle, G to V and V to G. What are these modes of operations? We will see that now. So, first is your grid to vehicle. So, this is the conventional mode where AC grid will be charging our electric vehicle battery bank. Okay. The other one is your vehicle to grid. Instead of behaving as a load, now our electric vehicle can behave as an distributed energy resource and it can supply active power to the grid during its requirement. When it can do that? When the vehicle is not used or it is parked in the parking lot and it is having energy. So, I can use the vehicle to support my grid such that its active power demand can be reduced. So, when this will be done? This will be done when the grid is having some peak loading where your power generation is insufficient to meet the load. Now, the recent term is your V2X where vehicle to everything. So, now your vehicle, instead of giving it back to the grid, what other options can be available? First is vehicle to grid, vehicle to home. Maybe we can use our electric vehicle to supply the domestic loads which are connected during the peak load of our grid, so that we are not relying on the grid to supply the power whenever it is having deficit in energy or when it is going to the peak loading condition. Then vehicle to building, vehicle to load, those things. So, vehicle can be used as the source and it can drive any type of local loads which are there with us. Okay. So, now these are the three popular terms: grid to vehicle, conventional one where we are just charging the vehicle. Now, these two are the modes in which we are discharging the vehicle and feeding the load. So, why this will be beneficial to us? So, this will be beneficial when the grid is having peak loading. Okay. So, when it is having peak load, so during that time we will be discharging the electric vehicle and feeding the power into the grid, and we will be reducing the stress across the grid. Okay. So, this will be helping the grid to mitigate its peak load demand, so that our voltage and power will be regulated. Okay. So, we know that whenever there is a mismatch between the voltage generation and the load, there will be fluctuation in the voltage as well as in power quality. Okay. So, assisting utility operators with voltage regulation, reactive power compensation and active power regulation. Okay. So, in our electric vehicles, when we have this converters which is bidirectional, we have seen that we can maintain the active and reactive power flow. Okay. So, when we are going for reactive power compensation to improve the power quality or to help the grid whenever it is having an low power factor, so we can give the reactive power so that our power factor will be improving or the voltage profile will be improving. Okay. So, how this voltage profile is related to our reactive power, that we have discussed just now while discussing the closed loop control. So, here the reactive power compensation I can do it by using the vehicle. Okay. So, that can be done irrespective of the mode of the vehicle, that is irrespective of our active power. That is what we have seen. Both active and reactive power are perfectly decoupled, because generally we use our DQ frame control where, or the decoupled current controller, where our active and reactive power can be independently controlled. So, what is the meaning of that? when my electric vehicle is charging, then also I can supply the reactive power, and the other case when my electric vehicle is discharging, obviously I can supply both active and reactive power simultaneously. So, this is what is the benefit of the grid support. Okay, so we will come back to this in more details when we go into the power system aspect of this grid integration of electric vehicles. There we will come back to these topics and discuss in more details. So, load balancing. Now, this whenever there is an peak loading condition, I will supply the energy present inside my electric vehicle to the grid. Whenever there is an excess energy, I will be using the vehicle as a load, or I will be charging the electric vehicle. So, during the off peak periods, I will charge my vehicle. Whenever there is peak loading, I will discharge my vehicle and give the power to the grid such that it gets limited or the load on the grid gets reduced. Financial benefits. So, as this concept is evolving, so we can have monetary benefits to the EV users if they are supporting the grid while it is having the peak loading. So, that will be an additional benefits the EV users can get. So, why this is required? Because nowadays we are going into more and more renewable energy sources which are intermittent in nature, or their generation cannot be predicted with 100% accuracy. So, during the mismatch, there is a high possibility of your power mismatch, or whenever we are having peak loading, that is when the generation is not sufficient to meet the load demand. So, during those cases, these EVs are more necessary to improve the stability of our grid. So, that is why this concept of vehicle behaving as a source has come into picture. Then now charging station architectures. Okay. So, in this case we have two popular type of architectures. First is depending on the source available with us. First is your AC connected charging station, where we will have the input as AC signal. Okay. So, in this it is popularly used because generally we have AC grids. So, we can directly connect our charging stations to the AC grid which is available with us. Now, uses reliable protection and metering, because AC grid is our conventional grid, or we have that since long. So, we have protection mechanism and ways of measuring the power being consumed and metering it. So, those things are readily available with us when we go for AC connection of the charging station. What is the limitation of this one? So, as we know, the EV has a battery which is a DC source. So, we will be requiring DC to DC converter at every charging point. So, for every charger we will have this DC to DC conversion stage requirement. Now, lower overall AC efficiency. Okay, so whenever I have AC, so first I have to convert it into AC to DC stage, then after that this DC converter. So, stages of conversions will be increasing when I go for AC type of connections. So, that is why the efficiency will be less compared to the next solution where we will have DC connections. Okay. So, when I have AC connections and my load is variable DC, so I have to convert AC into an fixed DC, then from this fixed DC to an variable DC. So, as the number of stages of conversion is higher, so we will be losing some power at every stage, so our overall efficiency will be decreasing. Now, DC connector stations, so here it will be superior efficiency will be there. Why? Because we have reduced the number of stages of conversion, because our load is DC and we have a source which is DC. So, single centralized rectification stage. So, in the previous case we required our AC to DC conversion everywhere. So, whereas in this case we have a DC source, or we can have a centralized rectifier stage which will be giving us the fixed DC. Okay. So, we can have this option with us. Now, facilitates the easy integration of your renewable energy and storage. So, what is the meaning of that? We have battery energy storage systems also, where we will be using the battery banks to support the grid or the charging stations whenever it is having peak loading or when the generation is not sufficient. Renewable energies. So, what are our renewable energies? The popular ones which are used in India are your solar and wind. Solar is a variable DC source, or the energy generated by the PV panels will be DC, but it will be in variable in nature based on your maximum power point tracking. So, that is your MPPT. And the other source is your wind, so which generates AC, but it is at variable frequency. So, what option is available with us? We convert this variable frequency AC into an DC, then from DC to an fixed frequency AC, so that it can be connected with our AC grid. Now, if I have a charging station which directly has a DC port, so what benefit will be there? When I go for PV integration, I can connect the DC which is generated by the PV panels to the DC bus directly, and for our wind energy, just variable frequency AC can be converted to DC and connected at the bus. Okay. So, that is why it is much easier for us to connect the renewable energies at the DC bus compared to the AC. Okay, because it will be requiring more stages of conversion, or more converters will be required when I go into AC then back to our DC for charging our electric vehicles. So, these are the two options available with us. So, AC and DC. So, AC is more popular because readily available grid is there with us, the conventional grid is AC grid, but in near future when we have more and more renewable energies, so we can have DC connected charging stations which may be self sufficient, or which can behave as a microgrid by itself and have 100% renewable energy supported charging applications. Okay. So, those are emerging topics. So, there we can have in near future we can have DC connected stations. Now, our charging modes. Okay. So, here if you add different types of chargers. Okay. So, here there are broadly two different types, as we have already discussed, AC and DC. Okay. So, based in this whether we are going for AC or DC, we have different types of or different modes of charging. Okay. So, mode 1 charging. So, it is the simplest way of charging, as we see in our two wheelers, where we do not have any facility of communication between the electric vehicle and the supply equipment, or the power supply which is present. So, you can see the mode 1 over here. Okay. So, in this case we do not have any type of communication, only power cables are there, that is earth, line and neutral. So, 3 terminals, single phase charging. So, this is the most common one for our two wheelers, where we have just an 5 ampere or 15 ampere plug depending on the rating of our motor which is available in the vehicle. So, and the battery bank. So, we will be having this mode 1, the simplest way of charging, but there is no communication protocol between our electric vehicle or EVSS. EVSE stands for your electric vehicle supply equipment. It is not recommended to use because we do not have any type of communication between these two components. Now, next mode is our mode 2. Here if you see, the only difference lies in between, it has an communication pilot terminal, or there is some inbuilt protection and control circuit inside this. From when we shift from mode 1 to mode 2, we get this additional protection and control. So, it will be having a portable cable which can be connected or plugged into our electric vehicle to charging it. Then it is recommended for home charging, where because we have this low power input supply which can be connected, but it has an additional facility of protection and control compared to the mode 1. Then mode 3. So, in this mode 3 we will have a dedicated charger. It has a dedicated charger which will be taking the AC as input. It may be household AC, or it can be an 3-phase supply which is available in the apartments. So, in this it has separate charger for every vehicle. It has an improved control system because a dedicated charger is there. Whichever protection and controls I want it, I can just use it inside the charger. It is used for your commercial charging, where we will have 3-phase supply and we will be going for this mode of communication. Okay. So, these two are your domestic modes. It can be your domestic or commercial mode of charging. Then your mode 4, that is our DC charging. Okay. So, if you see in this all 1, 2, 3 modes, we have an intermediate conversion stage, whereas in the mode 4 we have this directly, we can connect it to the battery because our mode 4 is a DC source based charging. Okay. So, here in this DC charging, it is usually used for fast chargers. Okay. So, it is our fast charging mode, or the, if you see the power rating also, it starts from 2 kilowatts, it can be having more than 200 kilowatts of power as on today. Okay, so this is the commercially available rating with us as on today. So there is research of increasing it further and further so that our charging time reduces. It is used for your commercial charging. So as it is having an such high power rating, so there is no point of having it in the domestic usage. So it is restricted to the commercial charging, where the vehicles can be charged is at as low time as 10 to 15 minutes. Then our various types of battery voltage and capacities. Okay, so two wheelers, 2W stands for your two wheelers, three wheelers. Okay, so the voltage is relatively less over here compared to the four wheelers, 48 to 72 volts. Okay, based on the battery capacity. Okay, so battery capacity is nothing but how much the vehicle will be running for charge, or once we charge it, what will be the distance to be covered before the battery gets discharged. So more is that, more will be our battery capacity. So here it is two wheelers, this is for three wheelers, and now if for our four wheelers, e-cars or electric vehicles, light motor vehicles. So in this we had initial generation, it was restricted to 21 kilowatts, where the battery bank was rated to 72 volts. Okay, now in second generation we have increased it further to 350 to 500 volts, and the power rating, if you see, it has been increased. Okay, so what is the benefit of getting increasing this power rating of this battery capacity? That is, the vehicle will be covering more distance per charge. Okay, so once I charge it, I can cover more longer distance. More is the battery size, more with the distance covered by it. So in the second generation, now we have 350 to 500 volt as the battery voltage. Now it is being targeted to increase it further to 800 volts, so that the range of vehicle can be further extended. Now here the power levels of your chargings. Okay, so here if you see, for the low power charging, this is the normal charging mode. In this, power level is less than 7 kilowatts. Then the second mode of classification is our 7 kilowatt to 22 kilowatts. In both the cases we can have AC and DC also. Then here high power charging. So in this high power charging, it will always be restricted to your DC, because we cannot have an high power converter on board, because it will be having a higher volume, or the space occupied by the converter will be higher. So always your high power chargers will be off board, or the charger will be located outside the vehicle, whereas low power chargers can be present on board, or we can make everything mounted on the vehicle, because the size and the volume of low power converters will be less. So this is used in your commercial parking lots, where we want the vehicle to have downtime as low as possible, where LCV stands for your light commercial vehicles. This is your medium commercial vehicles. Okay, so for your, for suppose your, so pickup trucks, those things can be having this facility of your high power charging. Now your connectors. So if we see the connectors, or our charger cable will be having an end terminal, which we call as your charger connector. So these charger connectors are also of various types. So in this we have CCS type of connector, CHAdeMO, type 2 AC, then our Indian standards, Bharat DC-1, Bharat AC-1. Okay, so based on the voltage ratings, if you see, the corresponding voltage ratings are given over here. So what is the meaning of this one? The number of charging points and the number of charging guns available with us. Okay, so in this, as we go for the different type of charging modes, I have to select the appropriate charger connectors. Okay, so let us see that in more details in the next few slides. So before that, some examples of your practical high power chargers. First is our solution from Delta, which is 100 kilowatt. Okay, so what are the ratings of this one? Input voltage is our three phase AC supply. So the output voltage can be from 50 to 1000 volt, and it can supply a maximum current of 200 amperes. Output power is 100 kilowatts. Okay, and it has two types of connectors. Okay, or it is compatible with CCS1 or the CHAdeMO type of air connectors. Okay, then the other one is your 240 kilowatt solution, where the input voltage is our conventional AC supply. The output can be ranging from 200 to 1000. Okay, so it has a maximum current capacity of 200 amperes. Its power charging power maximum is 2 kilowatts, 240 kilowatts, and it has compatible with CCS2 and CHAdeMO. Okay. So now these are the popular electric vehicles which are available in Indian market. So and their ratings and the range which are given over here. Okay, so we have seen what is the meaning of the range. More is the battery capacity, more is the efficiency of the drivetrain or the converter components which are present inside the vehicle, more will the range of that vehicle. So here battery capacity is given, motor type, which machine is used. So we in the next few lectures we will be going into the motors which will be used inside the electric vehicles. There we will see these motors in more details, PMSM and NDR induction machine. Your maximum power which can be generated by it, maximum torque and the range claimed by each of the models. Now your multi-port chargers. Okay, so obviously as we have seen that the chargers as in today are rated to 240 kilowatts and we have some solutions beyond that also. So in those cases our conventional three-phase VSI, they will not be able to supply that amount of power, or else what will happen. So we will be requiring higher and higher series and parallel connection of devices, which put several limitations. When we go for series connection of devices, they will be putting a restriction on the maximum switching frequency. Why? When we have series connection devices, they should exactly turn on and turn off. That is, their dynamic characteristics should also be same, which is not possible. Any two devices will have slight variation in their characteristics. So when I go for series connections, I have to go for some specialized mechanisms, and which will be adding to the cost of the system. Besides that, it will put a maximum limitation on the frequency. So what option is available with us? So why we are interested in voltage scaling? Because when I increase the voltage, I will be reducing the current. Okay, so if you have seen, when we have gone for fast chargers, we have increased the voltage compared to the AC chargers. Okay, so why we are increasing the voltage? Because the current will be reducing. If the current is reducing, the losses or the efficiency becomes better, because I square R losses, which will be the main cause of our reduction in the efficiency in the chargers. So if I increase the voltage, the current will be reducing. So if I want to increase the voltage without going for series connection, the option available with us is to change our front end converter from an to three-phase VSI, conventional three-phase VSI, to an multi-level converter. Okay, so here the first solution which is shown to us is a diode clamp multi-level converter. Okay, so where its popular application is in two areas. When we go for fast DC chargers, where the power rating will be higher, which will be mandating our series connection of devices, and we do not want to go into series connections. So we will be replacing our conventional three-phase VSI by an multi-level converter. Second is when we want multiple vehicles to be charged together, where it will be used in our public charging stations. There we will be having multiple charging points so that multiple vehicles can be charged simultaneously. So that our vehicle waiting time will be less. So whenever a vehicle comes, discharge vehicle comes, it can go and connect to an empty charging port which is present with us, and it can charge itself, and after that it can leave the charging station. So in near future we will have this public charging station as a replacement to our petrol pumps which we have as in today. So in that case we want more number of charging ports. So we can have a centralized AC to DC conversion stage which will be of very high power. Then from the DC bus which we have obtained, we can connect multiple DC to DC converters and construct multi-port chargers or multiple charging points for simultaneous charging. Okay, so that's what is the meaning of multi-port. That is, multiple output terminals will be available. So we can have a centralized multi-level converter which will be rated to or designed to handle high power, and we can have various DC to DC converters to supply the electric vehicles independently. And the second stage is, or the second application of this type of converter is when we have requirement of 240 kilowatts or higher power ratings of the charger. There we prefer for multi-level converters. Okay, the first example of our multi-level converter is shown over here, that is your diode clamped multi-level converter. So why it is called as diode clamped? So if you see, we have these points which voltages are fixed by using your diodes. Okay, so that's why the name is given as your diode clamped multi-level converters. Okay, so we will continue from this point in the next class. Thank you.